Okay, let us start with the price of the stock. Stock is also called underlying. So we have this is time axis. This is stock price S. So right now we are at time t. So this is now. And finally we will arrive at time large t. So stock price will change, fluctuate, and finally we will get certain value at time large t. Okay, we will call this value st, and this time we'll call it this value as sub small t. Okay, and what we can do is we can let's assume that we can purchase an option, and option, let's say we can purchase call option on this stock with strike price k. So we have strike price, let's say somewhere here, strike price k, and this call option, it's not free, it will cost us some money, but what it will allow us to do is it will allow us to purchase stock at time large t for k dollars. So let's assume that stock goes price of the stock goes above k. Then it's very nice if we have call option, because then we can purchase stock at k and immediately sell it at st and make a profit of st minus k. On the other hand, if for example stock arrives below k at time large t, in this case it doesn't make any sense to exercise this option to buy stock for k, because instead of buying it for k, we can just buy it at the market price, and there is no point in exercising the option. So if we write profit from the option, it's maximum value of 0 and st minus k. So if st is less than k, then we don't exercise it, and if st is more than k, then we we get this profit st minus k. So that's basic information about call option, and now what we would like to do is to calculate the probability. Let me go a little. So let us now calculate the probability that st is larger than k. So we would like to calculate the probability that our call option expires into money. And so how how we would calculate this probability, and let me note that at what point in time we calculate this probability. So we are sitting here at time t, this is now, and we would like to, so we are now at point t, small t, and we would like to know what is the probability that our call option will expire into money. So I will explain how to calculate it. So what parameters we have? We have strike price for the call option, K. Also we know the price of the stock at present time. Okay, and to do this calculation, let us assume that stock follows geometric Brownian motion. So geometric Brownian motion, let me talk a little bit about it. So well, how I understand it, there is a large company with huge capitalization, and well, stock price of this company is equal to capitalization of this company divided by number of shares. Okay, and essentially it's maybe multi-billion-dollar company, a large one, and we have small trades. So people are trading stocks of this company. They purchase and sell stocks in this company. So because but these are not large, we assume that these are not large transactions, and they cannot significantly affect the stock price. And in physics it's somewhat similar to the Brownian motion. When we have a large particle and this large particle is bombarded by smaller particles, and as a result this large particle, the motion of this large particle is called Brownian motion. So it's a random motion with certain properties. For example, if we calculate displacement, average displacement of this particle, it's equal to, I consider 3D case 6d, where d is constant times t, time. So something similar is going on the stock market when people are trading stocks, and also probably not only trades, but also news. Different news may affect the price of the stock and other events. Stock of the company is like this heavy particle bombarded by smaller particles. So it's somewhat similar to physical picture of Brownian motion, and that this idea was introduced in early 20th century, and then it was rediscovered, I guess, around 50s, and was successfully applied to stock market. So let's keep this in mind and use this fact. So so we assume that this stock price S follows geometric Brownian motion, and this geometric Brownian motion, it has parameters, two parameters, mu and sigma. Okay, so what are this mu and sigma? If we consider our physical picture, let's assume that certain force is acting on this particle, constant force. Okay, so this certain constant force is acting on our large particle, and so it wiggles and waggles around, but it also has a systematic constant force acting on it. So essentially mu is the parameter which represents this constant force acting on the particle, and as far as I understand it, it's something like, if you consider, well, let's consider stock market and stock of one company. So for example, company has capitalization of $10 billion, and we all know that inflation is going on all the time, and prices are rising all the time. So well, let's just take one of the factors, and so sales of the company will grow and its capitalization will grow just because of inflation, for example. So this constant force, well, one of the components of this force is inflation, for example. So mu represents something systematic, and sigma represents this chaotic motion back and forth of this particle, and this wiggling and waggling of the large particle. So this is sigma. And in finance, this mu is what we call instantaneous rate of return, and sigma is called standard deviation. So how we would understand instantaneous rate of return and standard deviation? It can be understood as follows. So again, let's draw the picture for price of the stock. So price of the stock at time t is equal to st, s sub t, and let's measure it at time t plus delta t, and let's assume that it okay, at t plus delta t, it's st plus delta t. So we can write a rate of return, continuously compounded rate of return, as follows. R is equal to 1 divided by delta t. We are just interested in this time interval. Natural logarithm of st plus delta t divided by st. Okay, this R is called instantaneous rate of return, and but I mean these quantities are constants, but this quantity is actually a random quantity. Okay, why is it random? Because how we would measure it is we would take several t's, maybe even tens or hundreds of t's, different time points, and calculate R. So we would have a series of rates of return. So it's a random instantaneous rate of return. And then we would find this constant mu as a just expectation value of R, this random variable, and sigma we would find just as a standard deviation of R. And also, to give you better idea, if I just work a little with this equation, I can write it as R dt equal to log of st plus delta t divided by st. Then I can put exponential function and I get st plus delta t is equal to st e in the power of r delta t. So we see that here R is continuously compounded rate of return. So that's where mu and sigma come from. And so now let's go back to our problem. Okay, let's go to the clean page. Okay, again, stock price as a function of time. Okay, so we are here, and we want to calculate something about time large t in the future. Probability that option will expire into money. So here, because stock, we assume that stock follows geometric Brownian motion, we have to make assumptions. We cannot say for sure what as stock price at time large t is going to be. We don't know it. We cannot say that it will be here or here. We will have a distribution. So what we have here is, we know that st, we know st, so we have this distribution is delta function, right? It's peaks at the value st. But as for s at time large t, we will have a distribution. It's going to be distributed somehow, and we know that k is a strike price, and to find probability that option will expire into money, we just need to take this probability distribution and let's say this probability distribution is p of st, or let's call stx. So we have distribution of x. So then we just need to integrate from k to infinity dx p of x, and then we will find probability that that call option will expire into money. So how to find this distribution? So now the question is how to find this distribution of the stock price at time large t. Well, what we already know will help us in the following way. We assume that stock follows geometric Brownian motion, and we know these parameters mu and sigma. So these instantaneous rates of return, mu and sigma, they give us something, they give us information about something, about stock price at time t plus delta t, where delta t is small. But we need to, and it will give us distribution at this time of the stock price. But we need to scale it to large t. We are interested in finite t minus t, not small delta t. So how do we do it? First of all, if we have instantaneous standard deviation sigma, then when we move to a finite time difference, we will get sigma is going to be replaced by sigma times square root of t minus small t, and this can be easily understood because remember in Brownian motion displacement square equal to in 3D 6D times time interval. Let me write it again. Displacement square equal to 6D t minus t, and so if we just look, so this is square of the displacement, but it's also essentially if we take square root, okay, and if we write sigma as standard deviation is essentially square root of x square minus average of x square, and average x is 0. So essentially here expression for sigma is written. So and we see that sigma scales as square root of time, so square root of time interval. So we can easily understand this. And what about instantaneous rate of return, mu? Looks like mu should be easily scaled as mu times t minus large t minus small t. But in fact it's not correct, and let's see why. I'll briefly explain why. It's an interesting point here. So in fact this is not correct. In fact it should be replaced by mu minus sigma square divided by 2 times t minus small t. So what we see here is that volatility of the stock, or standard deviation, actually suppresses the rate of return on the stock, and this can be easily understood. By the following argument. Let's assume that we have stock which is sold for $100, and well, it's just, there is no volatility. Standard deviation is 0, and let's assume it doesn't, well, it can grow or it may not grow. It's not important for our argument. So it's just, constant and goes to 100. But what if this stock first grows? So we have volatility. It grows first by 10% to $110, and then it goes down by the same 10%, and if we take 10% out, it's going to be minus $11, so $99. So what we see here is that the stock grown by 10%, then went down by 10%, and well, intuitively price should not change, but in fact we see here that it changes and it goes down by $1. The same case we can consider. I'll just want to show that it's doesn't depend on the order of the operation. So first, if it goes down by 10%, we arrive at $90, and then it goes up by 10%. So 10% of 90 is 9. So we again arrive at $99. So what we see here is that just the simple fact that we have volatility, the very fact that stock price goes up and down suppresses our return on the investment. And I can let me show it in a very simple way why this happens. So let me just write well-known formula. So 1 minus x plus times 1 plus x is equal to 1 minus x squared, and we assume that x is small. So what we see here is that when stock goes down and then goes up, we have a small suppression of the rate of return in the long term. So and one can see here that one can first that multiplication doesn't, the result of multiplication doesn't change which operation we perform first. So so that's what we found now. I'm not going to go into more strict argument, but for our purpose of moving forward, we have our stock price and time axis. This is t, small t, large t, and stock price follows geometric Brownian motion, and so it has mean of mu minus sigma square divided by 2 large t minus small t, and standard deviation of sigma times square root of t minus t. So what this means is, if we write a rate of return on our stock as a natural logarithm of st divided by s small t. So this is a random variable, because st is constant, but s sub large t is has a distribution. What these values give us is expected value of r is equal to this quantity, and standard deviation of r is equal to this quantity. So these are important equations. Okay, and this equation yes, and I forgot to mention that we assume that it's very important, so I write it down. Assume that R is normally distributed. Okay, so it has a normal distribution. Okay, so and so this quantity R is normally distributed, and it's clear why it's normally distributed. I'm not going to make another video about it. I suggest a video. You may watch video on central limit theorem by Bionic Turtle. I think David Harper, and so he explains it nicely that no matter what distribution you start with, so let me explain it briefly. Let's say you have a dice, many dices, okay, and you can roll the dice, you can get 1 here, 5 here, whatever you get. So this distribution of one dice is very easy. So distribution of, you can get different numbers, right? You can get 1, 2, 3, etc. So it's just a uniform distribution, right? Up to 6. Okay, let me write 6 here. Okay, and so here we have certain distribution for one dice, which can be actually almost any distribution. But now if I have many die and I roll them and I look at the first average, so what I take all, let's say this one will roll to x1 value, maybe x1 is equal to this value, okay? This one rolls to x2 value, which is in this instance is equal to 5, etc. And I go to xn. And then if I take average of x, and if I now take, and then I can produce average x. Okay, and I can do these rolls many number of times, and as I get many rolls I will get a different value of average x. So this average x will have a distribution, and if I look at this distribution, it's going to be Gaussian, so or normal distribution. So it's not going to depend, it will not depend on what is the distribution of one building block, of this building block. Well, they are all the same, but doesn't depend on how this building block is distributed. If we take number, large enough number, you know, more than 10 or more than 100 of this die, and we roll them, you know, more than 10 or more than 100 times, then we will get, I believe, pretty decent normal distribution of the average. So this is this result is known in mathematics as a central limit theorem. I believe it was I believe it was proven by Kolmogorov, and so this is a very non-trivial and important result. And now returning to why I say that here we get for the return on the stock we get a normal distribution or Gaussian distribution. Well, in my opinion it happens, well, first of all it's not exactly true, and people who study it, they find that it's not really normal. But if we in zero approximation assume that it's normal Gaussian distribution, then how I can explain it is, again, we have this company, large company, and we have these small trades. So no matter how these small trades are statistically distributed, no matter what is the distribution of these trades, small trades, when we look at the cumulative effect of these trades on the stock price, we see that they produce normally distributed rates of return. So in zero approximation this model does work, and certainly it's a useful tool to, well, normal distribution is very easy to work with and calculate something. So even if we don't agree with these assumptions, still we can do preliminary calculations using this model. Let's now go forward and look what we got. Let's look at these two equations, 1 and 2. They are key equations to they will help us to get our result pretty quickly. So we see that R is normally distributed random variable with expectation value ER and standard deviation sigma R. But in fact, these are not only conclusion about this rate of return R, but if we keep in mind that S sub small t, that this quantity is constant, essentially it tells us something about distribution of stock price itself. And that's what we need, right? We need to compare it to strike price, and if ST is more than strike price, then call option will expire into money. Let's now let me go forward as follows. This is our equation. Call option expires into money if stock price at time large t is more than strike price. So if this is true, then let's take natural log of both sides, and log is okay, we have x, natural log of x, and it's a natural, okay, it's it's a monotonic function, and so one can conclude that if we take logarithm of both sides, we will have this equation, and then and we can also subtract natural log of S sub small t okay, and we arrive to this inequality, but this quantity is rate of return. So rate of return should be more than natural log of k divided by st. In this case, our call option will expire into money. But what is what is R? R is normally distributed with ER and sigma R. Equations for ER and sigma R are written above. So here what I would like to do is to transform this random variable R to also normally distributed random variable with expected value of, let's call new variable y, expected value equal to 0 and standard deviation equal to 1. So because this variable y is going to be easier to work with, we can arrive to this variable normally distributed variable y with expectation value 0 and standard deviation 1 in the following way. If we take R and subtract expectation value of R and divide by standard deviation of R, then we will get this new random variable y, which is randomly which is normally distributed with this with 0 and 1. Okay, so and if you would like, I can prove it, so it's very easy. It's clear that expectation value of y is 0. Just take expectation value of the right side, and standard deviation of y is also very easy. It's okay, it's requires a little bit of work. I don't want to waste my time. It's very straightforward to show it. Okay, let me show it, but let's take variance of y. So it's going to be variance of r minus er divided by sigma square r. And then what is variance? Variance is expectation value of r minus er, k minus expectation value of okay, this expectation value is 0. Okay, and we arrive to expectation value of r minus e of r. Too many brackets here. Okay, and this thing is sigma square of r, so we arrive to 1. So so now if we have this inequality, let's transform it to the variable y, to the inequality for the variable y, which is normally distributed with average 0 and standard deviation 1. So it's very easy to do. R minus average value of r should be more than logarithm minus the same quantity. Then we can divide by sigma of r, because sigma of r is positive, and so what we got on the left hand side is this variable y. So we arrived to the equation that y should be more than natural log and divided by sigma of r. So the only change I would like to make is change the sign of this equation. So I would like to multiply it by minus 1. So I get minus y, and since I multiply by minus y both sides of the inequality, its sign should change, and here I get er minus log k divided by st sigma r. But because y is symmetric, we can introduce the quantity z, right, which is also a random variable with expectation value 0 and standard deviation 1. And so this equation transforms to this one. And probability that this z is less than. So because this random variable is normally distributed with expectation value 0 and standard deviation 1, we can write there is a special function for it, right, called cumulative normal distribution function, and this is exactly cumulative normal distribution function of this quantity, right? And so now let's just substitute. Remember, E of r is equal to mu minus sigma square over 2 t minus t, and sigma of r is equal to sigma square root of t minus t. Okay, and so let's write final equation. Probability that call option expires into money is equal to cumulative normal distribution of in the denominator sigma t minus t, and in the numerator we have mu minus sigma square divided by 2 t minus t minus, we can as well write plus, just a minute, plus log of st divided by k. So here is our answer. So here we found the probability that call option expires into money. This was a call option with a strike price K, and we assumed that stock follows geometric Brownian motion with instantaneous rate of return mu and standard deviation sigma. Thank you for your attention.